Okay, so this is problem 9 from chapter 11 of Giancoli 6th edition. So in this problem they give us the mass at the end of a spring. Okay, so they give us the mass. Let's write down everything that they gave us. At the end of a spring that vibrates a certain amount of times per second. In other words, they give us frequency, and they also give us the amplitude. Okay, so these are all the things that we have, and then they come with some questions. So the first question is, what is the velocity when it passes the equilibrium point? So what is the velocity at the equilibrium point? We know that this is the maximum velocity. And what is the equation for the maximum velocity? Well, there are some that we can use. Using conservation of energy, we have the 1/2 of mvx squared is equal to 1/2 of k amplitude square. I could consider using this one, but among all the things that they gave us, they didn't give us k, the constant of the spring. So, well, I could go and try to find this constant, but let me look at other equations for the maximum speed. Well, from that analogy with the simple harmonic motion, the motion of the spring, and the uniform circular motion, we also found that Vmax is equal to 2 pi amplitude divided by the period. So this is a better one because we do have the amplitude and we do have the period because we have the frequency, right? I can have 2 pi frequency. So this is the equation that you can use to find the maximum velocity, the velocity when it passes the equilibrium point. Okay, then comes the next question, which is find the velocity, the magnitude of this velocity, when the mass is 0.02 in my case, a certain amount from equilibrium. Okay, so they give us this x, and they want to know what is the speed at this intermediate point. Okay, again, if you have very good memory, you can go straight to the equation that we found for the speed at an intermediate point. We found that the speed is Vmax and 1 minus x squared over amplitude squared, the square root of that. So all that you have to do is put the x here, put the amplitude that is given, put the Vmax that you just found, and find the V. Again, if you don't memorize these equations, you just derive them, which is, I think, a much smarter thing to do. How would you derive this equation here? Well, you know from conservation of energy that at that intermediate point, the combination of the kinetic energy plus the potential energy is equal to the maximal elastic potential, the maximal kinetic. No, I can use the maximal elastic 1/2 of Ka squared. From here, cancels the halves and try to find an expression for this Vmax. Also for this V at an intermediate point. So this is K amplitude squared minus x squared. Play a little bit with this, and we find that V is K a squared over m. Let me put V squared here. 1 minus x squared over a squared. This we know is the Vmax. You can see from here. So this part here is the Vmax squared. Okay, so then we found that equation that we just used. V is plus minus Vmax square root of 1 minus x squared over a squared. Okay. This is the equation for the velocity. Here I didn't bother putting plus or minus because in the WebAssign you're actually just going to enter the magnitude of this velocity. Okay. Very well, let's go to the next one. Determine the total energy of the system. So the total mechanical energy of this system. Well, this is very simple because what could we use? Well, we could use the maximum kinetic, for example. We could use the maximum potential energy. The best one to use is this one, right? Because we have the mass and we have the maximum speed we already computed in part A. All right, last part of this problem is to complete the equation that describes the motion of the mass, assuming that, so this is part D now, assuming that x is maximum, which means x is the amplitude, at time 0. So this information is important for us because it tells us if we should use a cosine or sine. So if x is maximum at t0, it means that we stretch the spring before to start the motion. Okay? So I'm going to use a cosine. So the x will be amplitude cosine of the angular velocity multiplied by the time. So x is equal to amplitude cosine of 2 pi frequency. This is the angular velocity multiplied by the time. We have the amplitude, we have the frequency, and so we are done with this equation, and this is the end of this problem.